Well, hey everyone, welcome to our virtual presentation about Rapids and GPU accelerated data analytics in Python. My name is Bartley Richardson. I'm a AI infrastructure manager at NVIDIA and senior data scientist. And also this presentation was made by Keith Kraus, also an AI infrastructure manager at NVIDIA and leads the cuDF Python development team. Really wish we could have been there in person with you today and interacted with you in person. It's always great to see everyone. It's always great to hear about all the exciting things that people are doing in person and just see the excitement. Hopefully we can do that again in the future. I'm sure we can. Until then, this is kind of what we have, and so would love to take just a few minutes of your time and walk you through Rapids and how we do GPU accelerated data analytics in Python and in the Rapids ecosystem. So to get started, I wanted to just put up here, this is Rapids, right? Rather than bury the lead, rather than make you wait all the way till the end, this is Rapids. It encapsulates the entire data science pipeline from data preparation and the thing that we all love to do, right? ETL, feature engineering, right? I know as a data scientist, that takes up so much of my time just to get to the really interesting part, which is model training and visualization, right? But accelerating that entire pipeline. So when you look at what we have, right, or what Rapids has, it actually has all of those components. So things that we use for analytics, cuDF, cuIO, ways to get data in and do feature engineering. Analytics that revolve around machine learning in cuML and graph analytics in cuGraph, as well as visualization tools like cuCrossFilter, PyViz, ecosystem, and supporting zero copy in-place integration with deep learning toolkits like PyTorch, Chainer, and MXNet. So let's back up just a little bit and let's say, how did we get here to all on GPU accelerated data analytics? This is a little bit about the data processing evolution. Some of you have seen this probably if you've been to one of our other talks, but just to remind you, really where we're going and where we've gone through this entire evolution is faster data access with less data movement. So we start back in the Hadoop world, right? We do some Hadoop reads, do a query, write back out, read, do some ETL, write back out, read, and finally we can do our machine learning, right? Transition that to in-memory processing with something like Spark, right? 25 to 100x improvement, less code, language is more flexible, primarily in memory, right? Take that and let's think about a traditional GPU processing workload where we're still doing that HDFS read at the beginning. Then we're moving that data onto the GPU, doing a query, doing some ETL feature engineering, right? We do a CPU write, GPU read, then we do that ETL, right? CPU write, GPU read, then the ML train. The thing you can see that's common in all of this, right, is there's a lot of reads, there's a lot of writes, there's a lot of data movement. But what if we don't have to do that movement? What if we could keep the data on the GPU and really eliminate or minimize as much as possible the data that transfers back and forth across host memory from GPU to CPU? And that's the idea of Rapids, right? Instead of doing all these reads and writes and movements, whether it's from disk or between GPU and CPU memory, we do one read at the beginning, an arrow read. We'll talk about how Rapids is built using arrow. Do our queries, ETLs, and finally our ML training. We can get 50 to 100x improvement using the same code, flexible language, and primarily keeping that on the GPU. Just some benchmarks up front, right? Faster speeds, right? Whether we're doing IO, data prep, or whether we're doing something like machine learning, this time with like an XGBoost model, or doing end-to-end computation, right? So we have there kind of the difference in timings between a 20, 30, 50, 100 node CPU clusters, as well as a DGX2 and 5 DGX1s. Right? And so you look when you're comparing a DGX2, right, to a 100 node CPU cluster, and you can read there at the bottom what the CPU clusters was. And this is on a 200 gigabyte CSV data set. End-to-end pipeline, 322 seconds versus 3,221 seconds for a 100 node CPU cluster. Even faster on 5 DGX1s that are networked using InfiniBand. And even though the speeds are faster, Rapids doesn't stay in place, right? We're continuing to improve speeds over time. So here you have Rapids version 0.2 versus Rapids version 0.10, right? So if we look just all the way to the end, all the way to the right is the end-to-end benchmarks. In Rapids version 0.2 on a DGX2, again, this is with that 200 gigabyte CSV dataset. This took us 322 seconds. Flash forward to Rapids version 0.10, which was 3 versions ago. We're on 0.13 as of this recording. We can now do that in 209 seconds, right? So shaving off, whole 100 and almost 120 seconds off of that. And this is really what Rapids is all about. It's all about speed, because speed gives you so many things, right? Speed gives you iteration. And as a data scientist, iteration is crucial to the workflow, right? In order to continue to run models, in order to continue to do feature engineering, in order to try new things, you have to be able to iterate quickly. And I know just from my own experience, it's super frustrating to kick off a huge job, think that you've got everything correct in your ETL and your feature engineering, only to come back and realize that you messed something up or something errored out. And you have to start that job all over again once you find the error. So speed lets us do iteration. It's also important to talk about ease of use, right? I'm a huge lover of Python. I love the Python ecosystem. There's so many great tools for data scientists that made by companies large, small, open source. It's a great ecosystem to be in, which is why I want to do data science in Python. Before something like Rapids, if you wanted to GPU accelerate your data science, that means writing C++ or CUDA code. And that's just not how we as Python developers or data scientists or Python users work. So really it's those together: speed, which gives us fast iterations, and ease of use. It's the way that a lot of people are winning a lot of Kaggle competitions. And in general, it's just the way to win, lowercase win, at data science. It's what enables the data science workflow. So with that kind of being the upfront and kind of the motivating factors for Rapids, let's talk about the components of Rapids. Let's go through these. This, I'm sure everyone's familiar with this, right? This is the open source data science ecosystem and all of the Python APIs that you're familiar with, right? Going all the way from data prep to visualization. You got Pandas, scikit-learn, NetworkX. You might flip over and do some deep learning, right? So you're going to use PyTorch, Chainer, MXNet. And then you got your viz, Matplotlib, Plotly. And then you can parallelize this, right, using Dask. And so I know a lot of people are probably familiar with this. And I want to really quickly transition to the next slide to show you that not much changes, right? Let me go back. Familiar Python APIs that we're all comfortable with. Rapids, open source GPU data science, right? And again, as I mentioned up front, for analytics, we have cuDF and cuIO, machine learning, cuML, cuGraph. We have integration with deep learning frameworks, and then visualization. And we still encapsulate that whole data science workflow. And yes, we can still use Dask to scale out. There's more to Rapids than just Rapids core. We're going to talk about some of that later in the talk. There's components like cuSpatial. There's another one called cuSignal for signal processing. There's another library called CLX, which is for cybersecurity use cases. Here, though, at the beginning, we're going to talk and focus on the core of Rapids, which are the things that let us do data prep in this model training. Quick detour, though, before we get much further, and let's talk about Dask. Everyone, or a lot of people, right, use Dask to scale out their Python workflows and their Pandas workflows, and we can scale Rapids with Dask as well. right? Instead of using cuDF, there's a package called dask cuDF. And it really is drop-in simple replacement to be able to scale out with cuDF the way you've already been scaling out with dask in Pandas, right? And so here's essentially a little chart here about how we would scale up to accelerate or scale out to parallelize. So down in the bottom left-hand corner is all the PyData ecosystem tools that you're already familiar with, right? Pandas, scikit-learn, NumPy. These are all single CPU, these all utilize a single CPU core and in-memory data, right? Let's say we want to take that and we want to not necessarily scale out, but we just want to accelerate that workload. Well, that's where we can use Rapids accelerated on a single GPU. Right? You really don't need, you really wouldn't have to use dask to do this. You could, but you wouldn't have to. Instead of using NumPy, you would use CuPy, PyTorch. Instead of using Pandas, you would use cuDF, thus so on and so forth, right? Now, instead of accelerating, right, let's say now you have a ton of data, so you want to start to parallelize. If we go down at the bottom here, what we would do typically with the PyData ecosystem is we would scale that out with dask. Right? Instead of NumPy, we would use a dask array. Instead of Pandas, we would use a dask data frame, so on and so forth. But now let's say you want to scale out, you want to parallelize, and you want to accelerate using Rapids. And that's in the upper right. You can do that all with Rapids and dask using OpenUCX, right? This is multi-GPU on a single node, which would be something like a single DGX1 or a DGX2, or you can do this multi-GPU across a cluster. Right. So all this to say is that you're not, limited by the size of a single GPU that you might have. Right? We get this question a lot. What about GPU memory? And we hear you. Right? If you have, workloads that fit on single GPU, that's great. You can use, Rapids and cuDF without dask. But if you don't, right, and you want to scale up and scale out, you can use the tools that you're already familiar with. You can use dask with OpenUCX to scale out and to scale up with Rapids. So let's talk about cuDF. We've been talking about it a little bit thus far. It's GPU accelerated data wrangling and feature engineering, right? That's what cuDF is all about. So when I talked about this at the beginning, right? If you're anything like me, and you're a data scientist, or even if you're not a data scientist, right? ML/DL engineers also can spend a hefty amount of time doing ETL and feature engineering. This is, upwards of 90+% of the time spent just doing this. And like we were talking about before, the slower the iteration is, the longer this takes, right? Because if your ETL pipeline takes an hour and you have a mistake or you want to correct something in it, you have to wait, at least an hour to figure out that you've made that mistake. You can't get as many iterations in the day. So on the left-hand side, we have what would typically represent a CPU-powered workflow. By accelerating that, you get what's on the right-hand side, right? You're able to focus more on analysis, less time spent on ETL, and you can just see by the alternating kind of red and green or red and gray bars, you can just do so many more iterations of analysis in a day. So really, really, iteration and speed makes you more productive from an analytics standpoint. This is the ETL Technology Stack in Rapids. It's important to note that this is all built on top of CUDA and C++. And we'll talk about that in a second. But then there's also Python bindings to that underlying cuDF and CUDA libraries that allow you to call and use all of the great performance and take advantage of that performance in a Pythonic way that you're familiar with. So like I said, you can have your cuDF any way you like it, as long as it's either C++ or Python. So here is libcuDF. And libcuDF is a CUDA C++ library. This really has the down and dirty CUDA kernels for doing things like sorting, group by, scatter, gather. They have optimized GPU implementations for these data types, strings, timestamps, numeric types. There's more coming. And then primitives for scalable distributed ETL, right? Written in C++, Thrust. And you can use libcuDF in this way. Probably most of us, though, want to use cuDF. cuDF is this Python library for manipulating these GPU data frames, and it follows very, very closely the Pandas API. And the idea being it's so close to the Pandas API, and we're going to walk through some code a little bit later. I'll show you the differences, that the differences should be minimal, right? It's just that basically we're hoping for, over 90% parity with Pandas from the API. And cuDF is this Python interface to the CUDA-C++ library, libcuDF, with some additional functionality, right? In essence, it lets you use GPU data frames the way you've always used them, right? Supports JIT compilation of user-defined functions using Numba as well. Just some Speedup, and this is single GPU, right? So a single GPU on a Tesla V100, that's a 32 gig card, versus an Intel Xeon 2.2 gig processor. So if you see operations like merge, sort, and group by, merge 970 speedup, 970 times speedup over the CPU, single CPU versus single GPU. Also included in libcuDF and cuDF are string support. We understand that strings are very important. I know, as a data scientist, and specifically as a cybersecurity data scientist, I use strings a lot. So currently in version 0.13, that's the most current release version of Rapids that we have as of this recording. We support everything from regular expressions, element-wise operations like split, extract, typecasting. We can support group bys, joins, and sorting all on string data. Categorical columns are fully on the GPU, and there's a native string type in libcuDF C++. Going further in 0.14 and on, we're hoping to continue to do performance optimizations and then support JIT compiled string UDFs. And you can see here on the right-hand side, there's just some comparison between rapid string support or GPU strings versus Pandas, and doing common things like making everything lowercase, finding, and slicing. Right? The slicing, you can't even see the bar. It's so fast. That's in milliseconds, by the way. Extraction is huge, right? Being able to load your data in faster just makes your whole workflow faster and easier and less of a chore. So again, we're accelerating I/O following the Pandas APIs, providing at least a 10x, typically more speed up. So we have a CSV reader from pretty much the beginning. Version 0.2 of Rapids was when we had a CSV reader. We have a writer now. We can read and write Parquet, read and write to ORC, and we also have JSON and Avro readers as well. We're also working to integrate GPU direct storage for bypassing any PCIe bottlenecks that you might have. So that's actually enabling us to read directly from NVMe attached storage into the GPU and bypassing those PCIe lanes. And like I said, the I/O is very fast. Right? So if you see here on the right-hand side, we have a single piece of data, the New York taxi cab data. I think it's about 2 gigs, 1.9 gigs. It takes 29, almost 30 seconds with Pandas, a little over 2 seconds with cuDF. Okay, so that's cuDF. It's very important. The first step before I can do anything in cuML is I have to be able to get my data into the GPU. I have to be able to read my data in. That's what cuDF is all about. cuDF is about supporting those types of Python operations that you want to do, those type of Pandas operations that you want to do. Being able to create new columns, being able to create new variables, right? Enhance your data frame, filter your data frame. All of that is possible in cuDF. cuML starts where typically we think the fun starts, right? This is the machine learning. This is where you want to get to. This is the whole reason, right? Again, cuML, part of our Rapids core. And when you think cuML, think scikit-learn, right? Essentially. This is the technology stack for cuML. And like you probably noticed, there's some similarities with cuDF. cuML is all built on CUDA and CUDA libraries. In those CUDA libraries in C++, we have the cuML primitives, right? So those are fully optimized in CUDA and C++. With the cuML algorithms, which are built using the cuML primitives and the CUDA libraries. And then, because again, it's useful to have these callable in a Python interface, you can have everything in the same notebook. We have Python bindings that enable us to have the cuML algorithms callable from Python. Let's talk about some of those algorithms. Right? So really, there's a lot here. We started in point 2 with just a few algorithms, and now for point 13, we have all of these. So we have common classification and regression algorithms like decision tree, logistic regression, KNN, support vector machines, linear regression and random forests are enhanced for point 13. We have inference, including random forest inference, which we're going to show you a little bit. Clustering, k-means, dbScan, spectral, all the way from things like dimensionality reduction with UMAP and TSNE, PCA, some time series analytics, cross-validation, hyperparameter tuning. You know, I don't have enough time to go into all of it, but there's a lot. There's a lot there. I really like this slide because it just makes it clear about how common we are making the APIs between Python, between the Pythonic APIs you're familiar with and with the Rapids APIs. So this is how I would do dbScan using scikit-learn. Right? I could make some data sets, make the common moons data sets, and then import dbScan, set dbScan up with some parameters, do a fit, and then do a predict. Right? And then I've got it. So I'm going to transition to the next slide, and I'm going to highlight in red the difference between the CPU version and the GPU version. I'll go back. CPU version, GPU version, right? Instead of importing pandas, import cuDF. You can still make your moons data set. This time, instead of making a pandas data frame, you're making a GPU data frame using cuDF. And then from cuML, you're just importing dbScan, and then everything else is the same. Right? It's really that easy in most of the cases. So rather than just take you through a ton of slides, I thought let's switch over and let's show you a cuML demo. I should mention that all of these demos are in our container that you can download. I did that on purpose so you can get it. So if you go to our rapids.ai site and you go to getting started, and you kind of scroll down, if you click Docker plus examples, and then obviously configure this to whatever your environment is, this will get you all of these examples, right? So you could go through all of these right now. You could pause this, you could load this up, walk through it with me, or you could do it later, obviously. But I purposely picked demos that were in here so you could follow along, or so you could at least dig into it, excuse me, when you're done. So that's there for you. I'll flip back over here. So once you've got it up and running, I just want to make sure I don't have any kernels running right now. Good. You'll kind of hit this directory structure, and we've got them broken down by what they are a demo of, right? So we're going to start in cuML, just because that's where we're at. And since we were just talking about dbScan, let's start with one about dbScan. I'm going to spare you me reading through this entire notebook, right? But really, what I want to do is I want to hit the highlights. And I want to make sure that I show you what we're doing here. So we're just going to do some imports here because we're going to graph things out. We need matplotlib. Let's make sure we have a GPU here. We do. I should tell you that I'm on a DGX1. So you'll see the 8 GPUs there. MVCC, it's there. I don't know why that command failed. But we're just going to load some helper files here. You just saw this. We're going to make a moons data set, right? And then we're going to visualize that data set. There it is. Again, just showed you how, just showed that. And this we're just using scikit-learn to do that with. Okay. We're going to do some k-means clustering in scikit-learn. Different clustering in scikit-learn. and then we'll graph that out. The only reason we're doing this is to show that, hey, these two different types of clustering don't really work well for this data set, right? I'm not going to dig into like all the data science behind that. There's text here if you want to go through that. But basically, like, we need a different way to kind of cluster this data. And that's where this density-based approach to spatial clustering called dbScan comes into play, right? Instead of relying on finding centroids and associating, different points with centroids like k-means does, dbScan can basically identify clusters of any shape, right? Any convex shape. Okay, so let's finally run that. Let's use the sklearn version, scikit-learn version, and we'll do a predict. And then we'll plot that, right? That's exactly what we would expect. It's exactly what was on the slide. Didn't take very long, right? But again, we don't have a huge data set there. So because data is increasing, how can we accelerate, right? So let's now show essentially a Pandas and a cuDF, right? So we're going to load from cuML, import dbScan. I'm just calling it cuML dbScan here, just so we can keep track of where it's at in the notebook. We'll do a fit predict and a visualization. And this is the cuML version of dbScan, right? Nothing. I hope it's nothing exciting because it's exactly what we would expect, right? It's exactly what we would expect with the CPU version. So now let's do a little bit of benchmark, right? Let's look at the GPU version versus the CPU version. So here we have, I'm just making a data set here, a random data set. Looks like 10,000 rows. I'm going to go ahead and make the GPU data frame, the cuDF, set up dbScan, and run it. And to do the fit predict on that took 29.7 milliseconds. Let's use the same data set to do it on the CPU. And what I like about running it in Rapids in the GPU, right, is you saw it took 29.7 milliseconds. I could just instantaneously run that and then visualize it, right? I could make all kinds of tweaks to either my data set, the features in the data set, or I could actually tweak, parameters into dbScan itself. And because I have that interactivity, right, really what this is letting me do is do data science at the speed of thought, right? I can continue that thought process. I didn't have to fill with all the words I just filled in here for you. I'm sure no one caught on. That's why I was filling. But I was filling for the CPU to finish, and it took 31.2 seconds. So 30 milliseconds versus 30 seconds. That kind of, and that wasn't even a huge data set, right? It was 10,000 rows here. That kind of is, I love this demo because it really shows with even a small data set, and again, I'm running single GPU here, right? Probably have a GPU that's capable of this in your computer right now. I could essentially, insanely accelerate my workflow and not let me have to stop and think about the rest of it. I'm going to close that. And I want to make sure I shut down this kernel. And let's look at another one. Let's look at UMAP. Now, if you're not familiar with UMAP, I have to be honest with you. I love UMAP. Right? It's fantastic. It's a dimensionality reduction tool, right? It existed before. If you're familiar with tsne, kind of similar in spirit with tsne, but NVIDIA recently ported it to the GPU, and it has a Python interface with it, right? So again, much like with the dbScan, I'm not going to go line for line through this notebook, right? I'm just going to set up a few things, make sure I have a kernel, set up a few things, add some warnings. We're going to make sure that we have the data, and for this notebook, we're going to use the MNIST fashion data set, right? Which, in case you didn't know, it's 70,000 grayscale images of clothing, 28 by 28. Really hope we have the same GPU. Nothing changed there. Okay, that's good. We're just going to set up some helper functions. This is going to help us load data in, download data if we don't have it already. I went ahead and downloaded the data ahead of this time, right? So we're going to set up the training and testing data sets. Make sure they're all correct. Yep, 60,000 and 10,000. Let's look at what one of them looks like. This is a sneaker, I guess on Nike. You can kind of see a swoosh there, right? Okay, so now we've got the data, but we got to get it over to the GPU. So there is a cost, there's a time cost in moving data between host, CPU memory, and GPU memory, and so we have to include that in the time comparison. So we'll time this. This is essentially going to create a GPU data frame out of the fashion data set that we loaded. And so it took a little over 2.5 seconds. And during that 2.5 seconds, what it did is it moved the data, I guess copied the data, from CPU memory over to GPU memory. And now that I've got it in a GDF, which is a GPU data frame, I can operate on it on the GPU. So let's do UMAP on it. And again, it's doing this dimensionality reduction. And why might we want to do this? Well, we want to try to maybe see if we can separate these clothing, right? Do these clothings kind of separate out into specific classes? So that took 1.23 seconds plus a little bit minus, yeah. Okay. Per loop, 7 runs, 1 loop each. Great. Let's have the classes. We're going to rerun this. We're going to rerun this embedding because sometimes this time it loses the variable. So we just reran the embedding. It's doing exactly the same thing as this did up here. It didn't lose the variable this time because it finished so quickly. And then we can actually visualize what this looks like. Right. So here's the fashion MNIST dataset. It's embedded using the cuML version of UMAP. Right. So you can kind of see the different pieces of clothing. And how they might cluster together. So you see sneakers, kind of this like outline right here of sneakers. You see ankle boots with sneakers also over here. You see t-shirts and tops kind of mixed in with pullovers and dresses, which would make sense for us, right? Notice how bags are fairly well separated, which probably don't look like other things. And then you've got coats and sandals, and notice how sandals right here, kind of clustered together with sneakers and with ankle boots, right? So even just by kind of a cursory look at this, it's giving us what we would expect. Right? Cool. If we didn't do the CPU version of it, but the GPU version here is roughly around 9.5 times faster than the CPU version. Okay, let's do one more. I know I mentioned earlier about forest inference and the new forest inference library in Rapids. It's really super cool. And what it lets you do is it lets you perform inference faster, right, than if you were to use the inferences built into things like XGBoost, LightGBM, those types of things. And it's all optimized on the GPU. Right, so let's get a kernel. And we're going to go through it from the beginning, right? So we're going to make sure we have XGBoost. We do, and again, if you install it from the Rapids Getting Starting page, you're going to get all of this. I just did this install this morning, so it's working. We're going to get a little helper function for training up a model, and we're going to get a helper function for predicting an XGBoost. And what we're going to do, define some parameters. And this is the nice thing about it, right? If you were to pause this right now, I'll wait. Welcome back, if you paused it, by the way. But if you did pause it and you went and got this, you could mess with this, right? You could change the number of rows. You could up it by a factor of 10, right? I'm going to stick with this. We're going to generate some data, right? And then we're going to train and predict, right? So we're going to first train, and again, remember forest inference is for inference, right? So we'll need a trained model. So I'm going to train up an XGBoost model, right? An XGBoost classification model on this data we just made, and I'm going to use it to do prediction on my validation set. I kind of blew through it a little bit, but I split the data set here using my train test split function, which is, I believe I imported somewhere up here. Yep. So let's go ahead and predict. There we go. Oops, did I do it? There we go. Okay, now let's talk about the forest inference library. The forest inference library, again, just for do inference. So I'm going to load the XGBoost model, that I just made. It's going to take it a second to load the model. And then once I've got the model in there, I'm going to predict. And I'm going to get the prediction using FIL versus the prediction using XGBoost. Right. So we'll just wait on this to import here. As an aside, I hope everyone's doing well. Right? Hope you're enjoying this as well as the other PyCon content. Again, would much rather be with you, so I could be taking your questions right now and we can make this a little bit more interactive. But at the end, we have our contact info. You can always get in touch with us on Rapids as well, on GitHub or on the Rapids Slack. Would love to hear from all of you. Okay, that loaded. Let's do some prediction using FIL. It went so fast, sometimes I have to do it again. There we go. So 2 milliseconds versus 15.7 milliseconds. Well, it's definitely faster, right? But the question is, does it give us the same results? Because if it's faster and it gives us the wrong results, it really doesn't matter. I mean, it's still faster, but the wrong results are never good. So what we're doing now is we're taking the predictions from XGBoost and the predictions from Force Inference. We're making sure it's the same amount. Yes, we have 2,000. And then we are using our array equal helper function to make sure that all of the values are the same. And we're getting the same predictions back using Force Inference versus using the XGBoost prediction. So it's a really great way to accelerate your inference, right? Even if we're, even before 15.7 milliseconds versus 2-ish milliseconds if I round up, that's kind of big, especially if you're going from something that is maybe not as critical real time to something that needs critical inference predictions at bandwidth in real time, right? Something like that takes essentially a factor of 10 right down is very, very useful for that. Okay, make sure I shut that down and we're going to go back. I talked a little bit, I showed you a little bit about it, right? But here's just some more benchmarks for you. I won't spend a ton of time on these. You can always pause it and look at it. Single GPU versus scikit-learn, right? And you can see PCA 120 times faster. You can see other things such as SVC using RBF kernel, 730 times faster over CPU. Forest Inference, I just showed you a little bit about Forest Inference, but again, we can do, I think the line here that gets me is we can do 100 million inferences using this Forest Inference library per second with 1,000 trees on a DGX1 for large sparse dense models. 100 million Forest Inferences per second with 1,000 trees. It's just that's awesome. And you can do that, at bandwidth, right? At line speed. And I talked a little bit about XGBoost. We work really closely with the XGBoost community to accelerate gradient boosted decision trees on the GPU. The default Rapids Conda meta package includes XGBoost. So if you go and you use the default Conda install for Rapids, you're going to get XGBoost. And XGBoost can seamlessly load data from cuDF data frames and cuPy arrays. Right? Version 1.0 of XGBoost launched with the Rapids 0.13 stack, which just happened not too long ago. Okay, we're on version 0.13 right now, marching towards 1.0. Here's what's in cuML right now. You see we have single GPU versions for everything on that list, multi-GPU and multi-node multi-GPU for a lot of it. Going into the rest of 2020 and the road to 1.0, we're hoping to fill in that with multi-node multi-GPU. We're kind of consolidating. Instead of doing multi-GPU, then multi-node multi-GPU, we're just going straight for multi-node multi-GPU because that will obviously work for one node as well, making it effectively multi-GPU on single node. Okay, cuGraph. We're moving right along. I love graph, right? There's so many things you can do in graph. Like I mentioned before, I'm a cybersecurity researcher and cybersecurity data scientist. It's really, really useful for me to view data as a graph, right? I can see what machines talk to other machines, what people log on to machines, what error messages exist between machines, what types of data is being passed back and forth. it's a really intuitive way for me as a data scientist to interpret my data. The problem has always been that graphs get really large, and graphs get really large, especially when you want to put a lot of features on the edges, right? If I have maybe 20 or so features as a feature vector that I want to embed as attributes into a property graph, that really, really complicates the problem. So enter cuGraph, right? I don't know if you're getting the theme here, but essentially it's cu for CUDA and then something, right? So cu data frame, cu machine learning, cuGraph. I don't know. I'm sure you got it. I just wanted to make sure that you got it. cuGraph, focusing on features and user experience. What does that mean? It means all of these things. It means huge performance. Being able to store and analyze up to 500 million edges on a single 32 gigabyte GPU. That's insane. Multi-GPU support, billions and billions of edges. Multiple APIs, providing a C plus API for application developers, and providing that Python API that all of us like for NetworkX-like compatibility. Obviously, seamless integration with cuDF and cuML, property graph support via data frames. And it's important to note here that cuGraph really, it's not its own thing, right? It's a way to interpret the data in a GPU data frame in cuDF as a graph or as a property graph. So you're not learning a different graph programming language. You're not representing the graph. There's not a different underlying representation for the graph. It's a way for us to interpret the data as a graph, right? And then a constant focus on growing the functionality, more algorithms, more primitives, and more utility functions. Let's look at a little bit about the graph technology stack, right? Again, probably looks very familiar to you based on CUDA with CUDA libraries. And then here we have our primitives, cuGraph BLAS, cuHornet, right? The cuGraph algorithms are built using those primitives and those underlying technologies. And then, much like cuDF and cuML, there's a light Python layer that provides the Python APIs. Just an important note, NVGraph previously was closed source. NVGraph, because we get this question a lot, has been open sourced, and NVGraph has been integrated into cuGraph. Right? There is a legacy version of NVGraph available to you still on Rapid's GitHub repo if you want that. What algorithms can we use in cuGraph? A lot. So there's community-based algorithms, things like Louvain, K-truss, triangle counting, K-core. There's things like weakly and strongly connected components, link analysis with PageRank and personal PageRank, link prediction, traversal, BFS, and SSSP, different measures of centrality like cats and betweenness, auto renumbering, really, there's so many great algorithms here. The thing that I got excited about the most was auto renumbering, right? Because previously you had to provide cuGraph with your vertex IDs that were sequentially numbered from 0. Right. And that's the thing that just caused me the most problems. I love to complain about it to the cuGraph team. Not anymore. Auto renumbering is there in the utility function. It's fantastic. It lets you get at these algorithms so much faster without having to worry about the renumbering. Just a few, I'm going to show you some code, but just a few benchmarks before we get started. This is single GPU versus NetworkX. Right, so we're single to single, and the reason, I know we're talking a lot about single GPU, single CPU when we talked about scale out, but the reason we're talking about this is this really applies to so many data scientists and Python data analytics users that we talk to. They have a machine by their desk and they're trying to use that machine, or they spin up a simple machine in the cloud. So there's a lot of single CPU versus single GPU comparisons that we can make, and this is to say that even if you don't have petabytes of data, you can still get speed advantages, and you can still get advantages in doing more and more iterations faster using Rapids. So here, just 4 different graph algorithms: Louvain, PageRank, BFS, and SSSP. And this is the performance speedup, cuGraph versus NetworkX. There's I think like eight different data sets here. Let's just pick one. Let's use the AS Skitter data set, which has around 1.7 million nodes and over 22 million edges. Something like PageRank. Let's choose PageRank 3309 Speedup. So that much faster than NetworkX. And that's actually a pretty nice size graph, right? That's a pretty nice graph. Again, single GPU. If we go to multi-GPU, we can talk about even larger graphs. So this is just for PageRank, and let's just go right to the bottom. This is the big data X8 data set with 400 million vertices and 16 billion edges, right? It's a 300 gigabyte CSV file. And if you look at these last two rows here, the first row, the next to the last row is on the GPU. We use 16 V100s for this. And PageRank for 3 iterations took us 31.8 seconds on there. If you look at the same data set, we used 800 CPU threads. This is 108 vCPU nodes using Apache Spark GraphX. This took us around 96 minutes. So 31.8 seconds versus 96 minutes, right, on a 16 billion edge graph. Now these are the types of graphs that we see in cyber all the time, right? You see these huge graphs, and I want to do these as a data scientist. I want to do these over and over and over again. I want to run PageRank over and over and over again. And this is actually one of our applications that we use for one of our use cases in dynamic network mapping. We use personalized PageRank, and we want to do it at every time interval. Well, making me wait 96 minutes to do it really puts a bottleneck on it. It really delays how much I can do. Being able to do it in 31 seconds, that's great. I can take a little bit of that hit to get maybe every 2 minutes. I can still do better than 96 minutes. So with that said, let's look at a small cuGraph demo. I just picked one. This is connected components. And really the reason I picked it is I just want to show you how easy it is to use. Right? This is all about Python, and it's all about the Python data ecosystem. And so I just wanted to show you how it is. We won't, again, just like the other ones, you have plenty of time on your own. These notebooks, the reason I've chosen them is they're so well written and so well annotated that you can follow along and do that on your own. It would just waste your time for me to walk you through all of this. But essentially, we can use weakly or strongly connected components. Okay. We're going to use this NetScience dataset, which is referenced here. Total of about 1,500 scientists, largest component of 379 scientists, right? So there you go. We're going to import the libraries that we need. Start a kernel. Yep, great. We'll read that graph from the file. The file contains an edge list, source dish, and payers. In that file is coordinate format, COO format. We get a future warning here that I'm not going to worry about thus far, but you can see this is what the data file looks like. It's got a source and destination. We're going to create that graph from the edge list. It's really easy. You say create a new cuGraph graph, and then you just call from edge list. You give it the GPU data frame, this guy. Label the source column and label the destination column, and we're done. It's easy to call things like weakly connected components. Boom. Total number of weakly connected components. And again, if you're a graph person or if you use graph analytics a lot, you'll get this. If not, really what this is showing is that all of the Python APIs are fairly simple and straightforward to use. We can get a size of the largest weakly connected component, what IDs belong to the weakly connected component, and then we can do the same thing for strongly connected components, right? Total number, total size, vertices that belong to it, right? And that's essentially it, right? You know what? We have a little bit of time. I did not plan this, but let's do PageRank as well. Full disclosure, I didn't run this before we recorded this, so let's see. PageRank is fantastic. It lets you measure the relative importance of a node in your graph relative to the importance of its neighbors. Right? You're probably familiar with it the most from Google and the PageRank algorithm used to rank web pages. I'm going to just go through it real quick. This is, we'll use this Karate Club data set. Just a little bit of prep work. This should already be installed. Our libraries from cuDF, cuGraph, and NetworkX. Grab the data, and let's do this in NetworkX. That was pretty easy. Pretty straightforward. Let's do it in cuDF. Read the data in, create a graph, call the PageRank. That's it. It's you know, a lot of times when we show this off, we get like, so what? I mean, that's the point. There is no so what. It's that easy. We can actually look at the results. Right? PageRank is 0.100, not great. Look at the top 3. There's kind of what our graph looks like. Anyway, just wanted to show you how easy it was to run PageRank as well. Okay. The road to 1.0 in cuGraph. You know, a lot of things are single GPU. Everything's single GPU. We do have multi-GPU PageRank. Road to 1.0, you know, filling in multi-node, multi-GPU PageRank, PPR, personalized PageRank, weak and strongly connected components, card, overlap, SSSP, and BFS. And like always, we always like to hear from you. What things are you interested in? What things are you kind of wanting to see as one of these? You know, do you really need multi-GPU K-cores, or someone out there that would love multi-GPU K-core? Please visit our Slack or visit our GitHub and ask us those questions. We'd love to hear from you. cuSpatial, right? If you're doing any type of spatial analysis, right, you can accelerate that using cuSpatial up to 1,000 times faster than CPU spatial libraries, C++ and Python APIs. I know you're getting tired of me hearing me say this. It's a running thread. Growing functionality and completely integrated into Rapids. This is what the cuSpatial technology stack looks like. Again, you're very familiar with this. Based on CUDA, cuDF, libcuDF++, thrust, Python bindings to a Python API. Here's the roadmap for cuSpatial and being able to kind of like roadmap that out. You know, the graph layer right now, cuGraph, extending it out to Dijkstra algorithm, routing, map matching. In the query layer, doing things like KNN, nearest neighbor, range searches and joins, right? For geo representation, adding additional space shape primitives that you have. Here's just some performance of cuSpatial. Point and polygon test, and again, you can kind of read this for yourself. The one that I like to see here is the Hauer-Sign distance computation. So 13 million New York City taxi drop-offs and pickups. That's an NYC taxi data set that most people are familiar with. The reference runtime we used was actually on GPU already, and using Numba to compile to GPU using a single T4. Took 416.9 milliseconds. The cuSpatial runtime using Python built on top of the underlying CUDA and libcuDF++ libraries, 7.61 milliseconds. So even going GPU to GPU, we see a 54.7 times speed up in cuSpatial versus the reference runtime. Even more if you're going from SciPy. Okay, cuSpatial, cuSignal. cuSignal, again, we try to keep them named pretty much up front. cuSignal is all about signal processing, right? Now, I know you're super excited. It looks different. Unlike the other technology stacks, this one is developed purely in Python with custom CUDA kernels written in Numba and CuPy, so there's no Python layer for this. Right? So no Python layer, but pretty much everything else is very similar. Here are the algorithms that are available in the GPU accelerated version of SciPy signal, different types of convolutions, filtering, Hilbert, resampling. You can read them for yourself. Waveform generations, windowing functions, spectral analysis like periodograms and spectrograms. And here's some performance, right? You can see the different methods. So fast Fourier transform, FFT convolve, correlate, resample poly, Welch, spectrogram, CWT. Here's the SciPy version of it. And the cuSignal version of it. So 28,000 milliseconds versus 92.2 milliseconds for a speed up of around 300x. And this was benchmarked on, you can see 1 times 10 to the 8, sample signals on a DGX station. Right? And again, all of these notebooks are available in the repo. Efficient memory handling is one kind of really key point of cuSignal. We leverage the CUDA array interface for seamless handoff between cuSignal and PyTorch. We also use zero copy memory using Numba's mapped array, so memory between CPU and GPU. cuSignal represents the marriage of deep learning and RF data, things like signal identification, anomaly detection, right, and scheduling. And again, you can read about all of these. Again, I don't want to delve too deep on these specialized libraries just because it kind of limits our audience. But it's a really, if you're doing any type of signal processing, we do it in cyber as well. Like we look for periodicity, we look for different chunks of periodicity, and we're leveraging cuSignal to do that. Right? So there's a lot of different things you can use this for. I do want to show you a quick cuSignal demo here. So I've got the let's get a new kernel. I've got the cuSignal end-to-end notebook up here. So again, it came with that repo. If you go to cuSignal, you got an end-to-end example right here. So I'm gonna just go ahead and get started. Okay, I'm gonna go ahead and make some functions on the CPU and the GPU. So I'll make a few functions to generate a signal. And then ensemble those signals. And then on the GPU, I'm going to make the same functions. GPU function to generate signals, GPU function to ensemble those. This is just going to allow us to kind of change the parameters. You can play with these if you want. I'm going to leave them to the stock. Okay. And then we're going to go ahead and assemble those signals. We're going to use the CPU ensemble and the GPU ensemble to do that. So let's look at reshape using the resampler to upsample by 2 on the CPU, around 3.8 seconds. On the GPU, 21.2 milliseconds, right? Running a periodogram with a flat top filter over each row of the ensemble. Right. On the CPU, 4.19 seconds. On the GPU, 352 milliseconds. And we can even do output, right? Let's visualize CPU output. Visualize a different GPU output, right? The point is here is that it's essentially exactly the same way to call it, right? It's the same way to call it. Okay, let's flip back over and let's talk about clicks. Clicks is a little different. It's not a package in and of itself. It's really a joy of cooking with Rapids. And CLX stands for Cyber Log Accelerators. And really, it's a set of use case examples, workflows, and integrations that target the cybersecurity verticals and horizontals. We build it using Rapids and other GPU-accelerated compute platforms. It's targeted really towards those threat hunters, those forensic investigators, the cybersecurity and InfoSec data scientists, built to integrate with major SIEMs, and includes examples of pre-built workflows for specific use cases. So the components of CLX are notebooks that we have mainly towards data scientists and data engineers, We have some different use cases like networking and log parsing. SIEM integrations that allow you to import and export data to and from your SIEM. Splunk integration, direct query. We're also working on an integration with Elastic. We have workflow and I/O components. So this would be, again, not diving into all the details with just giving you an overview, but the workflow and I/O components essentially let you package up a cybersecurity-based workflow and kind of pass it around without having to you can kind of box it all together. You don't have to look at it. You can just deal with inputs and outputs. It allows you to stack them in different ways and kind of exchange them with others. And then cybersecurity primitives that allow us to have accelerated functions on cyber data types. That's such as IPv4, DNS, hexadecimal, such as IPv6 and MAC addresses. Just a few of the use cases that we have. One of them is this dynamic network mapping. And really the whole name of the game is we take data from a lot of different sources, either from Splunk or direct from the sensor. We ingest all of it into cuDF using cuIO. We run different graph analytics, PageRank, and community detection on it, and then we get an output of it. And essentially it's everything that is on your network, what it is, what we believe it to be doing, who owns that device, those types of things. Using something like our workflow and I/O modules, you can actually go from this piece of code, right, to something that looks like this. This is our Splunk alert workflow. But this is essentially how you could take something like this and you could package it up. So instead of having to look at this code and kind of go through this, you can encapsulate all of that into a workflow and then call your workflow to enable this to run over and over again. These are benchmarks for our dynamic network mapping. So again, the number of rows, these would correspond to the number of kind of entries in that graph. So 20 million rows, 10.2 seconds to do this. And again, this was single GPU. We have yet to benchmark it multi-GPU using the multi-GPU PageRank. A different one, security alert analysis, where we essentially look at all of your different alerts that you're getting and try to extract new information from them. Same type of workflow. And the key here, right, is that we're using Rapids to do all of this. This is our benchmarks. And if you see right off the bat that the majority amount of time is taken up by this reading from a Kafka producer into this pipeline, we are working on accelerated Kafka reading. That's being added to libcuDF and cuDF in the near future, right? So 300,000 alerts, took 3.0 seconds, but as soon as we get that accelerated Kafka reading, we're going to be able to take this down and run that in line. And again, this is single GPU, right? Single GPU Tesla V100. Something else we're really excited about in CLX is called Cybert. It's a way to parse your logs where you don't need to write regex for them. You just throw the log at a pre-trained and fine-tuned BERT model. And we're parsing with a micro F1 over 0.999 at over 1,500 raw logs per second. That's actually increased since then. This is what the pipeline looks like. There's a training phase, and then there's a parsing phase. I won't go into all of this, but essentially we're using Rapids and PyTorch. So we're leveraging the interoperability between Rapids and other GPU packages like PyTorch and DLPack to go to and back from them without copying data, right? So again, maintaining that speed of light analysis. Here's our inference and performance. And again, these are kind of dated. We're working on a brand new GPU-based tokenizer or word-piece tokenizer. It's actually in the CLX repo right now. That will help speed up all of this end to end. But we're getting very high accuracy, very high F1 score. And even when at this bottom chart, even when we're doing log parsing and we remove values from the logs or we degrade the logs, we're still seeing a micro and macro F1 over 0.99, even when we degrade the log up to 5%. Okay, so that's a little bit about Rapids and what's in the Rapids kind of packages. Let's talk for a few minutes about the community. It's been great working, fantastic actually, working as part of the open source community. There's a lot of interest and just working with all of the open source contributors is fantastic. So I want to talk a little bit about the community. These are some of our ecosystem partners. We have a lot of different contributors. everyone from Anaconda to organizations like Walmart and Capital One, to Gunrock out of UC Davis, to early adopters like Uber and Booz Allen, Capital One, OmniSci, IBM, to other players in the open source ecosystem like Nucleo, and I mentioned XGBoost, Dask, and Apache Arrow. Who's building on top of Rapids, right? People like Nucleo that build high-performance serverless event and data processing, utilizes Rapids for the GPU acceleration. Blazing SQL, which is GPU-accelerated SQL built on top of Rapids. Streams, which we actually use in Clicks and a lot of people use, distributed stream processing using Rapids and Dask. Let's talk a little bit about Blazing SQL. It's fantastic to be able to write just SQL queries in a Jupyter notebook and have it be accelerated. So what Blazing SQL does is it accelerates those SQL queries reading from disk and bringing all of that into something like cuDF. Right? And you can see here the query times for TPCH queries. It's really easy. Your data can exist on disk, Parquet, CSV, ORC, JSON format. You create a new Blazing context. You give that kind of access. You point it to where your data is, and then you're just writing regular SQL. Select, star, from, blah, where, blah. Let's talk a little bit about Nucleo. Serverless meets GPU, right? So they provide kind of this real-time auto-scaling function. So you can use common services, you can use platform-specific controllers, pluggable log monitors, and you can do all this from an image repo. If you click on this link or kind of visit this link, there's a lot more information about it on the blog post on Towards Data Science, or you can go to Nucleo's website to look at that as well. You can deploy Rapids everywhere. We're in all of the major cloud providers, all the major CSPs, Google Cloud, Azure, Amazon SageMaker, Dataproc. How can you get started with Rapids? You can install Rapids using Docker, Conda, or Colab. If you're brand new to Rapids, though, what I would recommend is you use the Rapids release selector, grab the Dockers plus the example for whatever your environment is. This will get you started in just a few minutes. We have a ton of walkthrough videos, blog content, our GitHub, the tutorial notebooks, and our example workbooks. You can join us on Slack, Google, Twitter, on GitHub. You can ask and answer questions on Stack Overflow. And just for right now, I want to jump over. Rapids AI is our main website, right? So you can go here just to get started. Lost my pointer. Well, it's fine. If you go to rapids.ai, you can get started there. This is our GitHub, right? Rapids AI GitHub. You can kind of go down and look at all of our different libraries, which I mentioned. Are all right here, and then you can, if you kind of go to cuDF, kind of go to cuDF, you can go here and just look at file and issue, really kind of whatever you want to do. Here we go, pull request, issues. Great way to get involved there. But also a great way is through the Rapids getting started, right? You can get started on, hold on, let me just exit out of full screen here. Maybe that causes the problem. But I don't know what caused the problem, but it's fine. We're just going to keep going. Rapids.ai has all of your information. Easy to install. Here's our GitHub. The docs have been improved. Really easy to use, docs.rapids.ai. There's a ton of code and a ton of blogs, right? Much more than what I can go through right now. You can find us on GitHub, but a great place is also Medium, medium.com/rapids-ai. There's blog posts about everything we talked about today, cuSpatial, cuSignal, cuML, cuDF, cuGraph, Clicks, everything is there. You can join us on Slack, Google Groups, Docker Hub, Stack Overflow. And what we really want is for you to contribute back, right? submit issues, submit feature requests, get in there and start tackling some PRs, write some blogs. We love to know how you're using Rapids, right? Tweet at us. This will really help us shape the future of Rapids. We really want to know from you, users, what's important to you and what's not important to you, what's working well and what's not working well. Like I said, it's easy to get started. This is a little bit of a repeat. You can go there, go grab the software, join us. There's our Slack, our Twitter addresses, our websites for all of this. And you can, of course, tweet myself or you can tweet Keith, email us, and we're also happy to get you going. Right? So there's a ton of ways to get involved with Rapids. If I was using it for the first time, I would pull the Docker with the examples, start messing around with that. Take some of your workflows that you already have pre-existing, try it out. Right? All you need is a modern GPU, a modern NVIDIA GPU to do that. So Pascal or higher. You probably have access to one. If not, you can spin us up in any cloud service provider, and there's instructions on the Rapids website about how to do that. Right? So again, contact us, tweet us, let us know your questions, what you like, what you didn't like, what you like about Rapids, what you wish was in Rapids. We'd love to engage with all of you. Again, we're really sorry we couldn't be there in person. We're really looking forward to future PyCons when we can all be there. We can all share the really cool things that all of us are doing. We really want to hear how you're using Rapids and how are you doing data science. Thanks so much for your time today. Really appreciate it. Stay safe, everyone.